Okay, do I have everyone's homework assignment? Okay, so I have a question for all of you. So, on the syllabus, I have the exam as a week from Thursday. It's supposed to be next week. That's what we're discussing, is when we should actually have it. Because I've heard from many students that apparently this week and next week are the exam gauntlet, right? That's generally, no? Travis is like, no, I'm throwing everybody else under the bus here. But in general, I think that most students have a lot of exams this week and next week, including what I had scheduled. So I would like to propose an idea. So I believe that I can get through the end of section 5 and the rest of section 6, which I thought I had up on the board, and by the end of this week. So what I'm thinking is we're going to start the Cadence stuff next week, the Cadence labs, and then we would have the take-home portion would be after, so it would be the 13th, or it would be 20th. To give the take-home portion to do over the weekend. On the 20th, you would have that portion due on the 25th, and then you take the in-class portion on the 25th. My objective, of course, being to try to take some burden off of your exams so you don't have them all in a glut, and you have a whole weekend to just study for this one. The issue is, I'm trying to design the Cadence labs such that you have one lab every week that's due through Blackboard, and it's going to be different. You're going to be using those internet learning services, and in general, we're going to be switching from the TGO model to more of a flipped model, where you're going to be watching the videos, and in class, we're going to be going over what you learned, answering any questions, and then allowing you to have the rest of the time to continue progressing in the courses and in the labs. That would mean if I gave you the extra week that I would have the exam on Tuesday in order to continue the course progressing how I feel it needs to progress. I would want the extra lab to come around the subsequent Thursday, right? So that's the trade-off. So the reason I'm asking you what you would prefer. So would you prefer I give the exam next week and then you have a little more time to do the lab? Or would you rather have the extra week to kind of start progressing on the labs, and then Tuesday exam, Thursday lab? So choice 1 is syllabus as is. Choice 2 as proposed new schedule. So who wants to stick with what we're doing right now? Okay, so I have 3. So I have 5. Okay. So hold on, me. Okay, we got that number. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. All right, and who wants the new syllabus, the new proposed schedule? 1, 2, 3, 4, 5, 6, 7. So I have 20 abstentions. 20 people didn't vote. All right, so I heard somebody say I want a question. Hold on. Somebody asked me a question. Yes. Well, that's another question. So I theoretically could have because I'll get through section 6 by the end of this week for sure. Yeah, so I currently have it listed as the 20th, but that could be another thing if people want me to move it up to the Tuesday to make things easier. No? Yes?
For those of us who are in physics 2, we don't have a test next week, but the week after. So that means we'll have a test in here and in physics the same week.
On the same day.
Yeah, on the same day. So.
Okay. So we're avoiding physics 2. Is that that's the whole goal? Okay. So 25th, that would be the subsequent. So I would have been moving it right to the same day as your physics 2 exam. Awesome. It looks like there's no way I can take some of this burden off of you, right? Like there's somehow I'm going to inconvene somebody. Yes, Alex.
Was it next Thursday?
I currently have it listed as a week from today, I believe. Yeah. So the Thursday would be ideal. All right. So how about this? How about this? I will make you all a deal. I will post the take-home portion on Thursday after lecture. You'll have the entire time to do that. It will be due on Tuesday. And then the in-class portion of the exam will be Thursday. So that way you have the maximum amount of time to deal with the take-home portion and study. You don't have a conflict with one exam. You don't have a conflict with physics 2, which I hear is taught beautifully. So I think that's the best compromise. Because all students, once upon a time I was a student, we all used to think the professors used to get in hoods and get together and figure out the optimal time to torture the students, right? That's not what we actually do. You try to, there's certain dates where we have to have grades reported for ABET accreditation or or being able to provide you opportunities to withdraw or not. So there's dates that just make a lot of sense. But, okay, so that's what we're going to do. I will post the take-home portion of the exam after Thursday's lecture. You'll have the entire weekend to work on it. I think the biggest complaint I got from exam 1 was that the 2-day turnaround was a bit rough. So I was hoping to try to make it happen on a weekend this time, and in subsequent courses I will make it happen on a weekend, so that way. So I'm taking your feedback already to improve the course in the future. So I'm going to make it the weekend, due on the Tuesday. The in-class portion will be on the Thursday. I think you'll take less time because basically you're just going to be updating your resume. You're not going to be building a new one, right? You guys got my feedback and you'll be able to do that. So that should only take you, 15, 20 minutes. All right. So does that sound good? Any complaints? Yes, Emily.
Is it going to be the same thing with the take-home too, where there's questions attached that kind of?
Yes.
Okay. Cool.
Yes, it'll be the same concept. The reason I'm doing that, this is the first time I'm doing that, is because I feel as though it's a good way to actually I can document and reward you for actually studying for the exam. How many times you all studied for the exam and worked your butt off and felt it didn't translate into a grade? Well, that's in one way, because the original goal was to try to document how to apply for a job, prepare for the job interview, and then actually think like the process of a job interview. But what I found from the grades coming back was that it also, in general, rewarded you for actually studying for the exam. So that's why I'm doing it that way. Any other questions? All right, so we're going to finish up section 5, and then I think, let me download section 6 here real quick. It's right there. All right, so up to this point, we have discussed single cycle data path, we've discussed pipeline, and we talked about these concepts of hazards, right? So we had pipeline hazards. What are my 3 types? Structural is 1. And something with C, control, yes. Very good. So you guys are doing. Oh, by the way, that I always give that assignment on the pipelining. Think up your own reduced data path. I always give that assignment, and then I have that list of problems that you're not allowed to do. You're the first class that the entire class didn't do any of those problems, so that made me very, very happy. So you should be rewarded for putting forth the effort and having the integrity to do that. Right, so the question that I forget who asked it, but somebody asked a very astute question. All right, we have all these hazards, we have all these stalls, we have all this data forwarding. Well, what exactly is that? How do we actually do that in the data path? And so that's what we're going to cover today. So in order to fully understand what we're going to be doing with the Tensilica and System C and basic static timing analysis for the cadence tools, you really have to have a basic understanding of how exceptions and interrupts work and how virtual processes and multiprocessing work. So we're going to be going over that for the rest of Section 5 and into Section 6. So Exceptions and interrupts. An exception is an unscheduled event that it disrupts program flow. And then an interrupt is an exception that comes from outside the processor. So we're going to discuss what the difference between those is. Now I should also actually have a note there. So I should note that these aren't industry-wide definitions, that sometimes people use exceptions and interrupts as synonyms, and sometimes that they are used in different contexts. In the context of the textbook and in the context of this course, we will define them differently because I want you to understand the difference in how there's two different ways that you can interrupt program flow. So the exception is an unscheduled event that disrupts program flow. So in this case, in TGO 5.21, we're going to start describing what an exception and interrupt is. So where does it come from? There's an external, meaning it's coming from the operating system, or it's internal, meaning something physically generated by the data path, right? So the designers of MIPS chose to differentiate between internal and external interrupts, with an internal interrupt being a quote exception and an external being called an interrupt. So if you recall from the topical guide objective where we talked about all the 32 registers, and some of those registers were reserved for the OS kernel, so that's the operating system kernel. That means there's specific values that are going to be stored in those registers in the event that we have an exception or an interrupt. And that we're going to be learning about how those are used today. So an I/O device request. So we've been working on this data path, and we've been working on all these instructions. Eventually we wanted to do something, right? So eventually what's going to happen, and for those of you who are taking operating systems, I hope you actually get to this, where you're starting to talk about I/O device requests, where I am the keyboard, I'm using the keyboard, and the keyboard should actually, there we go, that's a good way of not running my knee into that. Anything like what I'm doing right now with the pen, right? I am somehow requesting the operating system to actually process this task. So when I run the pen here, I put my finger across the touch screen. So what's actually happening? It says, all right, I'm receiving an input from the touch screen, I'm receiving the static. It's telling me that at these specific points, I am putting my finger on the screen. I have it in red using this program. So what happens is the processor receives an external interrupt, and it says, all right, you need to process putting something to the screen indicating that there's a line here. So this is actually processing data. It's processing RGB values, it's processing location data. Every time that the screen goes through, it's constantly refreshing the LEDs in the screen, right? So the whole time the processor is running this screen, and here I am telling it to do different things. So all of this is actually happening in real time, which is an example, going back all the way to the byte addressing, of why do I need to be able to do offsets and calculate the values from the temporary registers, right? Why do I need to multiply by 4? Because I will not be able to guarantee what that value is at runtime. You know, this is an actual location. So these are actual, the way it works with keyboards and screens is these all have specific locations, right? And they all correlate to a number. It has some value in a doubly linked list array. So you actually you wouldn't know this number until I actually touch the screen. So the only way you can do that is to use the byte addressing concepts with pointers. The user invokes the operating system. We won't really deal much with this, but if for some reason the user invokes the operating system, it's an internal, meaning it's actually run by the code. It's compiler-driven encoding. Arithmetic overflow. These are the two that we're really going to discuss for the rest of this section. Arithmetic overflow. What happens when we actually have a value that exceeds the 32-bit value from our word, right? From our bus. That's internal, and it's an exception. An undefined instruction. So what happens if we have a bad compiler? So MIPS is dependent upon the compiler. It's a compiler-driven encoding of the micro engine. So I'm not just saying this definition over and over again for my health. What happens when your compiler designer is a bozo and you come up with an instruction that is not on your MIPS screen sheet? So you have a control value sent to the controller, and that 6-bit value is not actually something that we designed. Remember all those AND gates from 5.15? What happens when I get a value that's not in there and none of the values come out? Well, if we get the wrong thing, we can sense that, and that's known as an undefined instruction, and it's internal, and it's an exception. So 5.2, we actually have an exception program counter. So we have a normal program counter that tells us where we are in the instruction, in the set of instructions, right? If we have an exception, we need to stop the program, fix the problem, and then continue the program, right? So I need to know where that exception took place. And that specific instruction is known as the exception program counter, often called EPC. MIPS includes a register called the exception program counter to contain the instruction that caused the exception. The basic action is, upon receiving an exception, the processor must save the address of the, quote, offending instruction, like we're saying here. It's pointing, we have the PC program pointing to the address, we have PC plus 4, right? So if something goes wrong, we want the actual PC value. Because what's going to happen, we're going to be going over exactly what happens here in a moment. But basically, you flush out the data path, you send it up to the operating system corrects the issue, and then reloads the instructions, at which point the exception program counter says we need to start here because you need to still be able to guarantee complete operation of the instruction, right? In this case, when it's sent up higher and higher and higher through the operating system, eventually gets to the point where it can't be solved by the operating system, you get your blue screen of death. And oftentimes that 0x in that hexadecimal value that you see is the value of the exception program counter and the value of the error itself. So you have, what are you actually doing? You have your exception program counter and what type of event. So that's what the blue screen of death is telling you. So for 5.23, how do we actually indicate which one of these is? What our type of exception actually is. So we have two specific values in hex that we have 80000000 hex. So that's 8 bits times 4 becomes 32. I mean, that's 8 hex values, so that's 32. So we're actually going to be storing this into our operating system kernel registers. So we have two exception vector addresses. The undefined instruction, meaning that our compiler has generated an instruction that is not done by MIPS, has an exception vector address of 80000000 hex. And the arithmetic overflow has 80000180 hex. And the reason that we need to know this is here. To achieve this, you must modify the MIPS data path to have two additional registers, exclusive from the 32 registers on the green sheet, the error program counter register, which we've discussed before, and the status register. So whenever you have the blue screen of death, you're going to typically see two large hexadecimal values, and those are that. Where are the instructions? Where in the instruction memory the error took place, and why we had to stop. And so let's define those in 5.24. The status register includes a register that holds a field indicating the reason for the exception. And vector interrupts. The address to which control is transferred is determined by the cause of the exception. So what's going to happen is we now know something is wrong, and we go to a specific instruction that's stored in the vector address. When we go to that specific instruction, so in instruction memory, I'll draw it on the screen here. In instruction memory, you have this amount that actually operates your code. And then there's all this other code here. So we get to this point where we have these vector addresses. So what happens is we're running our code. We run into an exception. What ends up happening is we perform a load word where we're loading the value. We perform a load word where we're actually loading the value of the next program counter value to go down here and execute these instructions, which is basically interacting with the operating system to ensure proper operation of the machine. Does this make sense so far? So how is an exception handled in pipeline MIPS? All right, so since 5 instructions may be in the data path at any time, this causes another set of trouble. We have, let's say we calculate an overflow in arithmetic, right? That means our exception is determined in the execution stage. That means we have 2 instructions that are in data memory and write back that operated correctly, right? Which means that we want those instructions to continue going. We don't want, there's also instruction fetch, and instruction decode that we do not want to execute because the incorrect operation on that ALU may cause it to have incorrect values later, right? Like we did in that example where we had all the data hazards, instructional hazards, and control hazards, right? So we have to actually stop it. Also, and this is where things get really fun, multiple exceptions may occur in the same clock cycle. So there's a theoretical situation in which the third instruction that's in the execution stage has an arithmetic overflow, while simultaneously in instruction decode, we have determined that the next instruction is a compiler error where we do not have that instruction in the data path itself. That's our worst case scenario. So, I forgot my little stars here. This is it, right? Where is it? Yeah, 5.25. Right. The exceptions are prioritized so that the hardware determines which exception is to be serviced first. So, even though I know that it's on the screen, which one do you think we should service first in that worst case scenario? Think like engineers. I know it's on the screen. I know the answer's on the screen, but bear with me for a second. If I both happen at the same time, I have an arithmetic overflow happen at execution stage, and I have an unfound operation in the instruction decode stage, which error do you think I should deal with first?
Find it.
Hmm?
The where it's not found. Or you can't find it.
Why do you think that is?
Because you can't find it, and how are you gonna fix it?
Okay.
Could it cause the arithmetic overflow?
No, in this case it would probably be caused because of a compiler error. So here I have.
By the way, I might go to the unfound exception called or no.
No, it's in the pipeline, which means that in this case that I'm proposing here, the arithmetic overflow is the third of the 5 instructions, and the 4th instruction, so it's instruction decode, is your unfound operation, which means that the arithmetic overflow operation was issued first. So we have one out of 40. A lot of non-voters. I asked for an exam. I had half the class not voted.
Unfound instruction, because it could happen again.
Okay, so we have 2 for unfound instruction.
Could the arithmetic overflow have caused an unfound exception then?
No. The reason why is because the unfound instruction is actually it's an issued instruction where the opcode has a 6-bit value that goes to the controller, and the controller goes through all the AND gates, and none of the control signals produce a 1 on the output. So this would not be caused by the arithmetic overflow. The arithmetic overflow might be an instance where you're trying to calculate a branch address, or whether branch 0 or branch not 0, and that causes a control hazard. But that's not this case in the instance of an exception or interrupt. All right, well, I hate to say that you both are wrong, but you are wrong. Here's why, but I admire the attempt, because ultimately what you're thinking about is we have to find we have this missing instruction, and we can't complete the rest of the instructions to do that. That was your thinking, right? The thing is that the arithmetic overflow was issued before. So we have 2 instructions that were completed. Then we have this arithmetic overflow issue that we need to address first, because we want to have the correct values. So once we figure out what this next instruction is, we can have the correct values in the register to execute it. Does that make sense? Okay. So in short, MIPS sorts that the earlier instructions are serviced first. Likewise, if it was the other way around, where if I had a problem where we had let me ask you this question. Actually, no, I won't ask you this question. I'll just tell you. You cannot have a situation where it's the other way around. The reason why is because if you have a screwed up instruction in the instruction decode stage, it'll be flushed out and it'll never get to the execution stage. So if you have an arithmetic that will produce an overflow, it'll be stuck in instruction fetch. It will never get to the execution stage. Does that make sense? I'd be happy to explain that again. I know I'm throwing out a lot at you. All right. So the error program counter captures the address of the interrupted instruction, and the MIPS service register records all possible exceptions in a clock cycle. So the error program counter can hold 2 instructions. In the worst case scenario where I have an arithmetic overflow in execution stage and an interrupt at an unfound instruction in the decode stage. So does anybody have any questions about that?
Was that sorting the first exception, like prioritizing the first exception, that's something that would be more efficient to
I'm sorry, can you say that a little louder?
It's something that would be a faster thing to implement.
Yes, that's correct. One of the issues, and we'll get to this next section, is what happens when you have something called out-of-order execution. It just keeps getting worse and worse, right? Keeps getting more advanced. Why is this course called Advanced Digital Systems? Yes, Jake?
So why is it that the not found exception is happening before the overflow? Would the overflow not happen with the ALU?
All right, so my next little portion answers your question in detail. So the question is, well, why is it that if I have a unfound exception error and the instruction afterwards is an arithmetic value, why would that not be the case? So I want to walk through the actual physical details of what's happening in an exception, and that should answer your question. All right, so we have an instruction sequence here, right? And so we also have what's actually happening. So we have 26 and 27. These are our operating system registers that are reserved for the OS kernel. And we have our instructions to be evoked on an exception are like this. So what's going to end up happening is we do our offset. We go down 1,000 from 0. So this is our data memory. We get this value, and then we load this value into this register, or this value, 80000184 in the instance of a overflow. In the instance to register 27, and then we would call a set of instructions to be executed by the data path in the event of an exception. So what's going to happen here is we have our normal data path, right? So in this example, the overflow occurs during the add instruction. So the add instruction is occurring in the 4th instruction. Therefore, the instruction in the EPC is like so. We have our normal case where we had, So here's what's happening. Our overflow occurs here. So what's going to happen here is we have our hazard detection unit, and we are detecting to make sure that we don't have an overflow. Remember we had an overflow bit from the ALU way back in section 2 in arithmetic? So what happens is we have this overflow bit that goes to our hazard detection unit, and it will start saying, wait a minute, this is not good. We have an issue. So the flush gets rid of we're going to call this flush. So let's see here. All of these, remember we had our control signals, and I showed you the diagram previous lecture. We had this 0 here. And what happens is it flushes everything out in the event of a hazard, right? Basically, it doesn't, no memread, no memwrite, no regwrite. It won't update anything. So here's why this is important, and this is going to start to answer your question. Once it recognizes this, it's going to start pushing all of the values to 0, right? So everything beyond this, it's going to wait. So it's going to, instead of issuing all the control signals, it's going to stay 0. So this instruction's not doing anything, and this instruction's not doing anything. This instruction is going to be allowed to continue, and this instruction is going to be allowed to continue. And then as this instruction would normally propagate through, because the clock is still going, nothing is being done. I'm not writing it down in memory because I know that that value can't be right. I'm not writing back to the registers the next cycle because that can't be right. And I'm not allowing these instructions to propagate through. What we're doing instead is we're doing this store word operation. Recall here, we had actually executed a store word instruction where I actually would get 0, register 0. Remember 0 is just 0, so it comes out of here. We get the value 1000 from the sign extended value. It calculates that. We actually get that value. That becomes our 80000180 hex. That comes out and is put in this register. And then from there, it's actually doing a number of instructions. It's going to a different set of instructions, instruction memory, and using that value to communicate with the operating system to figure out what went wrong. So the flush gets rid of the add and the instruction, as well as the other 2 instructions behind it. Note how the OR instruction, which is this one, was allowed to execute, and so you see this OR is still being able to complete, and we're starting to insert bubbles, or known as no-ops. So the instruction then starts with store word 26, 1000 from offset of 0. The whole goal is to get that vectored interrupt from the data memory that's stored in data memory, and that's going to continue performing this operation. So then the next instruction will be store word 27. It's getting both of the vectored interrupts. And then what happens is we have our save register on our error program counter, which will tell us specifically what actually happened. In this case, because of the fact that it's going to be a arithmetic overflow, it's going to tell us it's going to be in the error program counter. So here's the difference in the event of an instruction, an unfound instruction. What's going to happen is we have our instruction memory, right? It's issued here, and it goes to the controller. The controller says, oh, no, right? And it's going to flush everything automatically. Then this instruction, and this instruction are going to be allowed to continue. If in the instance the next instruction, so remember we are here because we've broken up into stages. It says no. We go here. It says flush because we have instruction decode flush there, and everything else continues. If the arithmetic that would produce an arithmetic overflow is in the next instruction, it would be here, and it would go to this buffer. In the next stage, when this gets flushed, this is just going to get flushed out as well. It would not allow it to continue, which is why that instance where I was talking about, where the instruction decode, then the arithmetic being in these two stages, and you have to deal with both of them, is not physically possible. While I'm plugging this in, does anybody have any questions? I do have a question.
Prevents following instructions from being run.
I'm sorry, what?
The flush prevents following instructions.
Yes, because what's ended up happening is because the hazard detection unit is saying, all right, I have to prevent this one and all previous ones from being executed as well. All right, so that's the end of section 5. And so section 6, and this is going to be the last section of notes that I'm doing, everything else beyond this will be cadence, is virtual memory and multiprocessing. Now, I'm going to see if I can open that in here, because I think this will look better. Yep, that's what I thought. All right, so that looks cleaner. So up to this point, we've talked about ALU, memory registers, control, full data path, pipelining, memory hierarchy, whole 9 yards. You are now getting really close to becoming experts in advanced digital systems. So what we just alluded to is that we have this operating system that we have to deal with, right? And most of you have done some sort of Java coding, right? Yeah, most nods heads, a couple no's. So that's most, so that's yes. All right, so when you're dealing with Java, so I talked about procedural language and object-oriented languages, and C is a procedural language. And if you learn C++, it's an object-oriented language. Java is an object-oriented language. And so everything's done in objects. Now, the issue with Java, this is its strength and its weakness, depending on who you ask, is that Java tries to obfuscate having to deal with the compiler. The whole goal of Java is to install the Java virtual machine, and you can write Java code, and it will compile it down to any machine, so you don't have to worry about that. The pros are it makes coding a lot easier if you're not terribly familiar with memory mapping. The cons are that if you're not, it runs a lot slower because you have to it does the pointer allocation for you, the memory mapping allocation for you, and it also works as, uses main memory as a cache for secondary storage. Right? So here in MIPS data path, we are talking about, did I get rid of EpicPen here? I did. So, with virtual memory, it's a technique where we define main memory as a cache for storage. So what's actually going on here? So in MIPS, we can theoretically represent 2 to the 32 bits in memory, right? But oftentimes you're not actually going to have that, even though we are kind of getting closer and closer to that capability. MIPS was invented at the time where you have 4 gigabyte computers to run these large programs. It's a fair amount of memory to run a program. However, memory needs to be transferred back and forth in order to run multiple programs, like we were just talking about. Sometimes the operating system allocates the processor to I/O. Sometimes the processor allocates it to the program itself. And you have to move these back and forth and still use the same memory mapping. When you're using the Java virtual machine, it's actually going to tell you to it's actually going to allocate main memory and try to use it as a cache. So sometimes when you're running Java programs, you notice how sometimes they run slower. Well, now you know why. Instead of working with the faster registers and the faster cache, it's actually doing that data memory access constantly. So that's why, especially if you're an aspiring electrical engineer, it's good to know C and how pointers work, because that makes you very good at allocating memory, which makes your processor run much faster. Does that make sense? So, virtual memory, defined it here as a technique that uses main memory as a cache for secondary storage. So, what I've been alluding to here is these two main motivations for using virtual memory. So, allow for efficient and safe sharing of memory among multiple programs, and to remove the programming burdens of a small, limited amount of main memory. So we have main memory, and we have these non-volatile disks. Now, I'm not going to really go into RAID arrays in this course and how they work, but you should be at least vaguely familiar with what's going on there. So you actually have a physical disk, and then you import from the disk into main memory, and then we use our cache hierarchy to try to interact with main memory faster. And then we have our local registers that we use very quickly. So we have this very distinct memory hierarchy that virtual memory is trying to obfuscate, so you can take some of the programming burdens off. So, reason why I mentioned this, so the guy who actually invented virtual memory is a guy named Rudolf Gunst, and his dissertation was called Local Design of a Digital Computer with Multiple Asynchronous Rotating Drums and Automatic High-Speed Memory Operation. So what he's trying to do is take these address spaces in the rotating drums, which are now known as RAID arrays that you deal with in your computers, in the disks, and try to use those for programming. So here we define the program's address space as a separate range of memory locations accessible only to one specific program. So if you are taking operating systems, you're probably familiar with segmentation, paging and segmentation? No? So maybe I should teach paging and segmentation. All right, so up to this point, you're familiar with byte addressing, right? So we have a program that we have a certain amount of memory here, of which we have a certain array here, of which we have split this into 4 bytes that become a word, a piece of information, right? So how do we actually allocate this memory in there? There's 2 different ways. We have a specific page, which is as you recall, page is the smallest amount. Actually, you don't recall because I define it here. A page is a fixed length contiguous block of virtual memory. It is the smallest. I should define physical address first. A physical address is the physical location of main memory of a program. And a page is a fixed length continuous block of virtual memory. It is the smallest unit of data that transfers from the main memory and the non-volatile storage, so the RAID arrays. So here's what's going on here. In memory, you have a certain number of pages. In paging, the idea is that the program will use up a whole page, and if it needs more, it'll go into the second page, and so on. The drawback to paging is that, let's say I only need a little bit more than the 1 page. Well, then I have this whole chunk of memory that's just not being used, right? So segmentation, they try to get around that by saying, I'm going to allocate segments in the main memory to a specific program, specifically to the size of the program. So we have that. So we have 1 segment, another segment, another segment, another segment. But here's the issue. Let's say I am done with this program here. Well, what I'm going to do is I'm going to free up that space by putting the results back into the non-volatile memory, and now it's empty, right? So now it's empty, right? But let's say I have a program that needs this much space. Am I going to be able to fit it in there? So how they solve that problem is they use this amount to go into this portion of memory, and this part goes here. in segmentation, so it puts it in segments. The drawback to that approach is you have a lot of memory gaps eventually. And you have programs spread all over the place because you're trying to use up these segmentations as best as possible. So you're either going to have, so you basically pick your own poison, right? So a good programmer that understands how that works is trying to actually would use the malloc. So that's in C, it's called memory allocation. The program's called, function's called malloc, which you'll learn about later in this course, to actually properly allocate the memory. So you're doing an efficient use of memory, you're doing efficient segmentation. But Java does most of this for you. Problem is, none of the reason why it runs so slow is because it's using paging and segmentation. Yes, hey.
So when you're doing segmentation.
All right, forgive me. I'm just going to skip over paging and segmentation questions because it's outside the scope of the class. I can answer it in office hours or at another time. I just felt it was important to do that. The key detail that you should know for mastery of this material is understanding paging and page faults. Right? So a page fault is kind of like a cache miss. A page fault is an event where the access page is not present in main memory. So think about cache. You have a certain amount of cache blocks in the cache hierarchy. If you have a cache miss, you have to go to the main memory, right? So if we're using virtual memory, we're taking advantage of main memory as a cache, and we have these different pages, and we go, okay, well, I need this specific page in the virtual address, which we'll talk about in a moment here. The virtual address is an address that corresponds to a location in the virtual memory. So we'll be talking about the translation process. But basically what's going on is I have a virtual address which points to this main memory hierarchy that corresponds to the non-volatile memory. I have a specific page. I ask for it in memory. It's like direct or set associativity. If it's not there, I then have to do a page swap. Just like if I have a cache miss, I have to do all this, cache hierarchy and mapping. So a virtual address is an address that corresponds to a location in the virtual memory. So we actually have just like cache memory, we have the page offset is determined by log base 2 of the page size, and the virtual page number is determined by the address size minus the page offset. And we're going to be going over an example here in a minute of what this all means. And the physical page number is determined by log base 2 of the physical size. Okay, so we're going to start going into this example here. So this kind of puts together all of the different concepts that I've kind of gone over here so far. So example 6.1, given a 32-bit MIPS data path where the page size is set at 4 kilobytes. So it's an arbitrary page size chosen by the designer of the operating system. The number of physical pages allowed in memory is 2 to the 18th. Show how virtual mapping is performed. So this is a really good exam type question because you can give a fundamental understanding of how virtual memory works. All right, so the first things first, 4 kilobytes is a term that is actually used to correspond to 4096 because it's a power of 2, right? So our 16K corresponds to 16,324, right? And 64K actually corresponds to 65,536. So that can be, so when you hear 64K, they're actually referring to 65K plus. And the reason for that, in case you're wondering, is they're trying to maintain this, power of 2, and then correspond it to the closest possible value. So when 4K is there, that means 4096, because remember 2 to the 10 is 1024. 2 to the 11th is 2048, and 2 to the 12th is 4096. So that's the closest to 4K. So first things first is we use this definition that we had, log page offset and physical page number. Log base 2 of 4096, as we just calculated, is 12. So the first 12 bits, or I should say the 12 least significant bits, since we're big endian in MIPS, are the page offset. So think of this as similar to shift left logical, where I did shift left by 2, we perform for byte addressing. Because in byte addressing, we want to have 4 bytes correspond to a 1 word. And that's our smallest amount that we would have to represent data, right? So in this case, our page, which we would have a program, if we're saying that, what this means is if we have a page that's 4 kilobytes, that means the smallest address value is going to be 4 kilobytes, right? So that means every single time I move, if we think of it like address, and you're 4 kilobytes, if I want the second page, I wouldn't move to 1024, right? I'd have to move to the next level, which is 4096. That represents our page offset. The next step is the number of physical pages in memory, which is what we're using, either data memory or our non-volatile memory. It's 2 to the 18. Log of 2 to the 18 is simple. It's just 18. So that means we have the next 18 bits corresponds to those values. So what that's actually here, you see we have MIPS, we have a 32-bit value. We have a page offset of 12. And then we actually have an address of 20. So we have 12, we add 20, that becomes 22. So 32 minus 12 is 20. So we're now going to use those next 20 bits to calculate the virtual page number. I'm sorry, I should be clear. 20 minus 12 is 20. 32 minus 12 is 20, sorry. And then we have 18 bits to represent the virtual page number. So page offset is the size of the kilobytes of 4K. And then virtual page number, which I'll get to the translation here in a moment, corresponds to 18. So in the MIPS is everything is 32 bits because it's a fixed width. And when we do this MIPS we translate to the virtual address, we actually get the physical page number and the offset, which corresponds to these values. So you see the difference. We have 20 possible values. So the largest value in a 409, where we have 4096 represent our page, we could have 2 to the 20 of those. In this case, we've said we're only going to need 2 to the 18, which is why the difference here is 2. Does that make sense? So the way this problem works, the simplest version, for those of you who want to know, is like, all right, I'm going through here, page size is 4 kilobytes. I would say, all right, log 2 of 4096 is 12. Log 2 of 2 to the 18 is the number of physical pages. 2 to the 18 is equal to 18. So that means in the virtual address corresponds to MIPS, the 32-bit value, right? So what we're trying to do is actually say, all right, well, I could theoretically represent 2 to the 20, which is why we call it virtual. So there's actually 2 bits in the virtual page, in the virtual address, that are not representing anything, but we could. So when we actually translate it to a physical page, what we're saying is what we're actually going to have this value translate out here. So if we wanted to do a different version of this problem, ignore all that. That was something I added in 2 years ago. If I want to do this, if I wanted to say this was 1K and the number of physical pages is 16, then what actually happens is 1024 becomes 10, right? So this becomes 0 through 9. And then 2 to the 16 just becomes 16, right? So the virtual page number is 10 through 31. But that's not the way it actually works. We could do, in this case, it would be 10 through 31, so it would be 32 minus 10, 2 to the 22, right? But we only actually need 2 to the 16, or we can only actually represent 2 to the 16 in the virtual memory. So what ends up happening is this becomes 9 in the page offset, and this becomes 10. We add this would be 25. Do you see how that works? So you can say ... 10 to 25. Any questions? Yes.
So does that mess with anything for it to not be a 32-bit number? For it to not, the whole physical page number, page offset to no longer be 32 bits?
Well, you'd have to have some memory to exceed you actually have to have a physical memory that exceeds 2 to the 20, which is, when you think about it, an incredibly large number. When you think about what's, remember, 65, 536, that's, 64K. If you're getting up to, you're multiplying this by 128, 256, 512, and then 1024, right? So if you're saying 2 to the 18 is, that's 2 to the, I'm having a brain fart here. Okay, so let's think about it this way. So you have 2 to the 10, right? And that's 1096. So we have that number of 4 kilobyte blocks. So that's actually 2 to the 10 times here, which is 2 to the 12. So now it's times 2 to the 22. And a gig, so you have 104096. So now you're getting into megs here, right? So a gig just becomes that times 2 to the 10. So now you're representing 4 gigabytes. So when you have like 2 gigabytes of memory or 8 gigabytes of memory, that's what's represented in the actual hardware. And so you actually have to do page swapping. So now you're going into the actual digital memory. So that becomes, we have 2 to the 32, right? Remember that when we were talking about the possible combinations of ALU outputs? Remember 2 to 32 and how big it was? The same concept. Any other questions? All right, so ignore that. All right, so issues in virtual memory design. So what are the issues that we address here? So key decisions in the design of virtual memory systems. So that pages should be large enough to try to reduce access time. If the pages are too small, you have to actually do it's the same thing with cache memory. If you make the cache too small, you increase the access, the cache blocks too small, you increase the access time. You want to have a low page fault rate. So you want to try to take advantage of temporal and spatial locality in your coding. And then handle page faults in software since the overhead is low compared to disk access time. And so when you're actually accessing the disks, that actually becomes even longer. And so a page table contains the correlation between the specific virtual page number and the physical page number. So in the previous problem, and this will tie in everything we're just talking about, I think probably will ultimately answer the question I think you're about to answer about segmentation. When I'm swapping out pages, you're going to lose the order, right? There's no guarantee that when you swap it back in, it'll be in the same order that you had it, because the operating system it'll use some sort of algorithm, either least recently used or most recently used, or something along those lines. There's a number of different algorithms that are typically found for those of you taking operating systems, I believe it's chapter 13 of the Dinosaur textbook. There's a number of different algorithms for replacing pages. And you have to do this efficiently, which is why we're talking about low page fault rate. Do you all remember the term that I used? Starts with a T, when you have a lot of pages going back and forth? Thrashing, right? Land sharks, thrashing. Good when it's the defense, bad when it's operating systems. So what's actually happening here is if you do a very poor job of having two variables that are different pages constantly going back and forth, every time you access it, all right, well, it's a cache miss, level 2 cache miss, level 3 cache miss, data memory miss. Now we're getting to the virtual memory. Now it's a page miss. Now I have to swap the page. You have to put the page back in. Then I have to put it into data memory. Then I have to put it into the cache level. Then I have to put it in the local register. Got to go back to the other page. Got to go back to level 1, level 2, level 3, data memory, virtual memory. You see how that works? So if you're the actual definition of thrashing is if you're spending more time performing memory accesses than you're actually doing processing, then you're thrashing. So then this low page fault rate becomes very important. And one of the ways we do that is we do this page table, where we actually correspond the specific virtual page number and the physical page number. Now, if you look at example 6.1, which we just did, you'll see that the virtual memory space, the potential locations, is less than the actual locations. If the process attempts to locate a page that's not in the physical memory, that's a page fault. If it's not in that page table, the operating system will go to the disk storage and swap it. So we'll also define this term swap space, which is the space reserved on the disk. The swap space is the space on the disk reserved for the full virtual memory space of a process. So I have some process, I have some program that I want to do, and I have this swap space where ideally if I'm trying to allocate a specific program, I'd want to be able to swap the pages back and forth in that specific swap space. So we have that chunk of data memory, right? So here's where this becomes a pain in the butt. So now that you are starting to become more knowledgeable of advanced operating systems, let's think of one of the big challenges with this swapping. So I swap something out of the non-volatile memory. I put it into the data memory. That data memory contains load locations, right? So I have this instruction, these instructions that are saying I want to go to data memory and get specific pieces of information, right? By doing a swap. And what are you going to do? It's going to calculate the load address based on the pointer. So what you have to do in order to make those correlate is you have to update the data memory, you have to update the caches, and you have to update the page table to make sure that the same calculation in the instruction memory will get the new location in the page table, right? So operating systems can be very complicated. And the simplest way to do that, which is why I included in 6.11, is that you have to make sure the pages are large enough to reduce the access time, and then load page faults, and then handle the page faults in that way. And the best way to do that is to know how to actually code in a way that takes advantage of temporal and spatial locality and demonstrates a knowledge of the advanced digital system. And so one way we try to get around this is this concept of a transition look-aside buffer. I got rid of 6.15. Can you give me a split second here? I think I had a diagram that I wanted for 6.15. All right, so transition look-aside buffer is a cache that keeps track of recently used addresses in the physical memory to try to avoid access to the page table. So if we have these recently used accesses, this means that we don't want to try to, hold on. We have a recently used accesses. What that means is instead of trying to go to the page table every time, we want to use a local cache, which is faster, which contains the most recently used accesses in the virtual memory space. So that's 6.14. And let me see if I can find, Alex, what's the name of your textbook? It's the operating systems. Yeah, this one, Shilber, Schatz, and Galvin. I want to show this diagram is actually important. For some reason, I left it out of the page access diagram. Not this one, but that's process state. That's another. Why am I using Bing? Page fault. Images. This is it. Steps in handling a page fault. I use this exact diagram, except I hand draw it. If it ever comes up. All right, so this is TGO 6.15. And this is where we'll end lecture today. So what's actually going on here? So we have a page fault, and we have this page table here, and we have this operating system controlling our load memory. So this memory here is what we're communicating. So everything we've learned into this class is our microprocessor, which is what we're communicating over here, right? So what we need to do is we do a request, right? We look up our page table. We ask it, is the page I want in data memory? It is not. Well, then I tell the operating system that's called a trap. The operating system says, okay, well, all right, I need to go to the main non-volatile memory. I have to get a page, right? So now I have to go to the actual physical memory itself. This is the non-volatile memory. This is your data memory. You see the difference? So what's actually happening is I have to either put this in a free frame, or if I'm out of free frames, I have to take a frame and put it back. Then I have to update the page table, which means that I have to tell the page table where everything is, right? And then I can start here in this instruction. You all see how this works? So what's actually going on here in the event of an exception is that the exception is going to go to the operating system and say what's going on here. And while we won't really go into much in this course, it goes to something called the kernel. And the kernel will tell it how to fix the program. But in this case, I have page fault. I say, hey, I calculate my virtual address by determining my page offset and the actual size of the data memory. The page table tells me where it should be. I ask it, is it actually in there at the moment? If it says no, I tell the operating system. The operating system says, okay, the page is actually located here in the physical memory. These are the disks. It then puts it into the non-volatile memory. I either find a free frame. But the one thing that's not included in this diagram is if there's no free frame, I have to do a page swap. And then I have to tell the page table where it is. So this is different than cache in that cache uses directed and set associativity, right? Basically, you use the tag, index, and block in order to actually determine where it is. In this case, you actually have to have a page table. Now, since the page table is located in the non-volatile memory itself, we have to try to come up with a faster way to find the least recently used. So that's where we would include a transition look-aside buffer. It would go here first and says, yeah, it's actually right here. That works most of the time by taking advantage of the temporal and spatial locality. If not, it then goes to the page. The page would then go here if it's found. If it's not found, it then has to say, all right, operating system throws a trap. Operating system says, here's the page, brings it back in, swaps one out, update the page table. In this case, you also update the transition look-aside buffer, and then run the program again. Does that make sense? So in this case, I'm going to stop lecture here. This is, for those of you watching the video, this is 6.15. I apologize for not having that figure in there. I would redraw it by hand. And we're starting to do this because we're now starting to go past where the Patterson-Hennessy textbook is. You've now moved beyond the textbook.